Hello everyone, welcome to our channel. This is Dinesh MA, working as Assistant Professor in the Department of Electronics and Communication Engineering, Maharaja Institute of Technology, Mysore. In the last session, we discussed the JFET device, its construction, operation and the characteristics. And in this session, we'll discuss the drain characteristics of P-channel JFET along with the MOSFET device, its construction, operation, drain characteristics and transfer characteristics. Now let us get into the drain characteristics of a P-channel JFET device. In the last session, we understood that in the operation of a JFET, a P-channel JFET, we will be applying a negative voltage at the drain terminal with respect to source and a positive voltage at the gate terminal with respect to source. So let us consider the same points to understand the VI characteristics of the P-channel JFET device. Let us draw the circuit diagram first. So this is drain, this is source, and this is gate terminal. And here we'll have an ammeter and here we'll have the voltage source that will bias the device, and here we'll have a voltmeter connected. So this is going to give me VDS, and as I indicated, the gate to source should be positive. So let us connect the batteries like this. This is VGS and drain should get the negative voltage with respect to source. So let us have it like this, and this is VDS. So this is a circuit diagram what we have for the determination of VI characteristics. So now what we are going to do is we will be plotting how this ID, the drain current ID, varies with respect to VDS. So ID will be flowing in this direction. So let us plot ID versus VDS. So on Y axis we will have ID, which will be measured in milliamperes, and on X axis we will have VDS, which will be starting from 0 So this is VDS, and ID we'll have it in steps of 3 milliamperes. So now let us say like what we'll do is we'll vary VDS, and the corresponding change in the ID will be noted down for a fixed VGS. Let us say VGS is 0 initially, VGS is 0. Now when VGS is 0, we have understood in the operation of the P-channel JFET, when VGS is 0, there would be no depletion region, right? Because the junctions will not be reverse biased if VGS is 0. The junctions are going to be reverse biased only when we apply some positive gate voltage with respect to source. Now when we consider VGS is equal to 0, there would be no depletion regions penetrated into the channel region, so there would be easy current flow, right. So now when VGS is 0, as we go on vary, say for example when VDS is 0, ID will be 0. And as we go on increasing, rise the VDS voltage, there will be an electric field induced in the channel which makes the charge carriers drift. That causes the current to flow. So as we go on increasing the VDS value, there will be an increase in drain current. And once we reach a particular point, there will be small increments in the drain current, and after a particular point the current is going to be saturated. So VDS will not be having any control over IDS, so IDS becomes constant. Further increase in VDS will cause the device enter the breakdown region where current is going to be increasing rapidly. So this we call as breakdown region. So this is for VGS is equal to 0. Now what if I increase VGS? As I was just indicating, if I make VGS more positive or any positive voltage applied between gate and source will make the junctions at the gate channel A region, the junctions will become reverse biased, and this will make the depletion regions penetrate into the channel region deeper, and this will cause the drain to source current reduce. So let us do VGS. Now let us increase this to 1 volt. If I increase this to 1 volt, then what we'll have is current becomes saturated at an earlier value, and further breakdown region will also be attained at earlier value. So let us say this is for VGS equals to 1 volt. Further, if I increase the VGS, then again the saturation occurs at a more earlier stage, and the characteristics looks like this. So this is for VGS equals to 2 volt, and for VGS equals to 3 volts, the characteristics will look like this, and again the breakdown occurs at earlier value. So this is for VGS equals to 3 volts. So further, if we go on increasing the VGS value like this, so what happens is the depth of the depletion regions into the channel region will be more, and at a particular point the two depletion regions will touch each other and ID is going to be diminished. So maybe somewhere here it may look like this. For say for example VGS equals to 5 volts, so where the current is going to be minimal. So this is the drain characteristics of an P channel JFET. Now we'll discuss the concepts of MOSFETs. MOSFET stands for metal oxide semiconductor FET. So MOSFET stands for metal oxide semiconductor FET. So what we'll understand here is, first we'll understand the construction of MOSFET, and then we'll understand the operation, and then we'll understand the drain characteristics and transfer characteristics of MOSFET. Now there are two types available in MOSFET. One is called as enhancement mode MOSFET, the other one is called as depletion type MOSFET. One is enhancement type, the second one is depletion type MOSFET. So down the line during the discussion, we'll understand what is the difference between the enhancement type and the depletion type. Further, these two are subdivided into N-type and P-type devices. So in enhancement mode, we have N-type device and P-type device. Likewise, even in depletion mode transistors, we have N-type and P-type devices. First, we'll consider the enhancement mode device or enhancement type device for the discussion. And we'll be considering N-type enhancement mode here, right? So let us understand the construction first. So as the very first material will be having in the N-type, so this is for N-type. The type indicates the channel of the device. So the N-type enhancement mode device, it starts with a P-type substrate. So this is P-type substrate. So this is a highly resistive material is what we'll be having. Now into this P-type substrate will be diffusing highly doped 2 N plus regions like this. This is N plus region. This is also N plus region. Now after diffusing these two regions, then we'll be having a thin layer of silicon dioxide. This is SiO2 layer. Then after depositing this SiO2 layer, what we'll do is we'll make holes where we need to deposit the metal layer for facilitating the terminals. So we'll be creating holes like this on the thin layer of SiO2, and then here we'll deposit the metal to facilitate the contacts. So this will be working as drain terminal and this will be working as source terminal. Then between this source region and the drain region, so this is going to work as source region and this is going to work as drain region. So on this surface, what we'll do is we'll deposit a thick layer of polycrystalline silicon which will be working as gate region. right? So this is the construction of N-type enhancement mode MOSFET device. So what we have here is, as a base we'll be having P-type substrate into which two heavily doped N plus regions will be diffused, which will be working as source region and the drain region, and on the surface of this will deposit a thin layer of SiO2. So, and then we'll make the holes and will do the metallization for the sake of creating the terminals. So here we'll have the source terminal, and in this region we'll have the drain terminal, and between the source and drain regions we'll deposit a layer of polycrystalline silicon. So this is polycrystalline silicon, and this will be acting as gate terminal. Initially, when the MOSFET was designed or proposed, this was just a metal layer. This was not polycrystalline silicon. This was a just metal layer, just like this. So the name for this device given metal oxide semiconductor, because we have these three main layers, that is metal and then the oxide and then the semiconductor. This type of field effect transistor was called as MOSFET, metal oxide semiconductor. Earlier, and then later on, because of the advancements done, research been carried out, this metal cap was replaced by polycrystalline silicon, but still the name MOSFET has been used for this device. Now we'll understand the operation of this device. Now to understand the operation or working of this N-channel MOSFET, what we'll do is we'll apply an voltage at the drain terminal and at the gate terminal and understand how this is going to be working. Let us apply a positive voltage at the drain terminal with respect to source. So before that, here the P-type substrate, this will also be considered as a terminal, and this will be called as substrate or body or bulk. So all the same. So generally we call this as substrate. This can also be referred to by these two names, body or bulk. Now let us say here we have a positive voltage applied at the drain terminal with respect to source. Now because of this, what happens here is, this is N plus region which is getting a positive supply voltage here, a positive energy it will get, and this N plus region has got a negative supply voltage. Now what happens here, this is P region, this is N region, so this forms a diode here. Let me put it like this. This forms a diode, this also forms a diode like this, because this is N region, this is P region, and these two are connected. So what we have here is the N plus source, the P-type substrate and the N plus drain forms two back-to-back connected semiconductor diodes. And because this diode is this drain terminal is connected to positive terminal of the battery, this diode will be reverse biased, and as I indicated, this P-type substrate is highly resistive. So here I can also indicate a high resistive element between these two diodes. And because of this arrangement here, there would be no current flowing. And moreover, what we have here is we have a p-type material. So in the p-type material, what we'll be having is the holes will be the majority charge carriers, whereas the n plus regions have got electrons as the majority charge carriers. Now if I want the current to flow between drain and source, the electrons are what I need. So here, because of this p-type region, there would be no charge carriers, I mean the electrons that can flow from source and drain. So what we'll do here is, in order to make the electrons flow from source region to drain region, we need to apply some voltage between gate and source. What if I have not applied anything? Let me connect something like this. Let this be plus and this be minus. Let us call this as VGS. This is VDS, and this should not be left open. This should be connected at the source potential. Now what happens? If in case VGS is equal to 0, then again here that doesn't make any change. Now if I increase this VGS, say for example I'll make this 1 volt, then here I'll be having positive energy, right? So because here I have positive energy, the electrons which are available here in the p-type substrate will be attracted towards this positive energy, just like with the semiconductor diode. So all these things will be attracted towards this end, and here let me clear this. So what happens here is, so all the electrons that will come and settle down here, even the electrons from the n plus regions will be attracted towards this end. Now what is happening is the p-type layer will be converted into the n plus layer, and we say the channel has been created. So we call this as the channel, right? So what happens when VGS is equal to 0, this layer will be p layer and there would be no accumulation of the electrons under the gate region will be there. Now when I apply some positive gate to source voltage, this positive energy will attract all the electrons available in the p-type substrate under the gate region along with the electrons from the n plus regions. And this will change the nature of this region under the gate terminal. So this we call as channel region, and here the changing of the p-type region into n-type region, this process will call as inversion, right? And now because there is a positive VDS, there will be an electric field induced in this direction that will make the electrons drift from the source region into the drain region. When electrons are moving from source to drain region, the effective current will be flowing from drain to source region. We say IDS is flowing. Now VGS was set to 1 volt. What if I increase VGS? Increasing VGS will accumulate more electrons in the channel region where the conductivity of the channel will be increased. Remember, when VGS was equal to 0 or no VGS was applied, there was high resistivity in this region. Now, when there is a positive voltage applied between gate and source, this resistivity has been reduced because there is a channel formed. There is a conduction taking place. Now as I go on increasing this, more electrons will be accumulated under the gate region, so the resistivity will be decreased. So more the gate to source voltage, more the electrons will be accumulated under the gate region, more the conduction will be. So what I mean to say here is, as I go on increasing the gate to source voltage, the conduction in the channel region or under the gate region will be enhanced. So this type of device is called as enhancement type device. Right? And the IDS will be controlled by VGS in this case, and this can also be controlled by the drain to source voltage. So this is the operation of the enhancement type N channel device. And now we will understand the drain characteristics and transfer characteristics of the N channel enhancement mode device. So what do we learn here in the drain characteristics is how IDS is going to be varied, the drain current is going to be varied as we increase VDS for different voltages of VGS. So that is what we will be understanding. So let us draw this. So this is IDS in milliamperes, and here we have VDS in volts. So this is 0, 5, 10, 15, 20 and 25. And this is 2, 4, 6, 8, 10 and 12. So further also we can have. Now what we'll do is, if VGS is equal to 0, if VGS equals to 0, there would be no channel created and there is no question of current flowing. So if VGS is 0, there would be no current. So this is for VGS equals to 0. Now if I increase VGS by 2 volts for example, then what happens is there will be an increase of conduction in the channel region, and as we go on increasing VDS, the electric field will be induced in the channel and that brings some electrons towards the drain end. So there will be a small current flowing, and as we increase the VDS, the device or the current is said to be saturated and becomes constant like this. So let us say this is for VGS equals to 2 volts. And now as we increase VGS to another level, the conduction in the channel will be enhanced by a bit. So more amount of current will be flowing. So if I increase VGS, let us consider VGS equals to 4 volts now, then there will be enhanced conduction in the channel which causes more current availability flowing in the device. So this is what I am showing: more the VGS, more the conductivity, more the current, and again at some particular point the device is going to be saturated and the current is going to be constant like this. So let us say this is for VGS equals to 4 volts. Then again further if I increase VGS to another level, so that further enhances the conductivity of the channel, where I will be having enhanced current flowing in the device. So that may look like this. So this is for VGS equals to 6 volts. Likewise, As we go on increasing the VGS value, there will be enhanced conduction taking place in the device. So this is how the drain to source current varies with respect to changes in the VDS. So now this is the drain characteristics. Let us draw the transfer characteristics also. Transfer characteristics is what? How the current IDS varies with respect to changes in the input voltage VGS. Here VGS is considered to be the input voltage. So let us say here we will consider another scale. For VGS, this is VGS. So now as VGS is increased, we can see here as VGS is increased, the current levels have also been increased. So I can say as VGS is increased, what we can see is the IDS value will also be increased. So this is transfer characteristic of the N-type enhancement mode MOSFET, and these curves are the drain characteristics, which shows how the drain current varies with the variations in VDS. So this is the characteristics. This is all about the characteristics of enhancement mode N-type MOSFET. Now we will understand the P-channel enhancement mode device construction. So here we start with N-type substrate first. So this is N-type substrate where we will be diffusing P plus regions So these two regions will be working as source region and drain region, and above this will be depositing a layer of SiO2 and then we'll make the holes to create the terminals so that we can deposit metal layers. So here we deposit the metal layers. Right. So this will be working as source terminal and this will be working as drain terminal, and between these two source and drain regions will deposit a layer of polycrystalline silicon and this will be working as gate region. So this is the construction of P-type enhancement mode MOSFET, right. So the operation looks similar to the N-type device. So here too there will be no channel by default. So what we have is N-type layer, there is no channel available by default. So to create the channel, what we'll do is we'll apply the gate voltage that will attract all the holes available in the N-type substrate under the gate region and also holes from the source region. So that makes the channel, and upon applying proper voltage at the drain terminal with respect to source, the holes will be moving from source region to drain region so that there will be current flowing in the device. So this is construction and operation of the P-type enhancement mode MOSFET device. Now we will understand the depletion mode transistor. So the construction of the depletion mode transistor looks like this. Even here we will consider the P-type substrate first. I am drawing the N-type depletion mode transistor now. So we will start with the P-type substrate, and here we will diffuse two N plus regions, and in between these two regions we will be having channel region. So this is the difference between the enhancement mode device and the depletion mode device. In the enhancement mode device, the channel will not be available by default, it will be created by applying a positive gate voltage. But here in the depletion mode transistor, the channel region will be available by default. And above this, we will be having a thin layer of SiO2, and here we will make a hole for the sake of metallization, using which we can create the terminals. So this is layer of SiO2. And above this we will be having a layer of polycrystalline silicon. So this is polycrystalline silicon, and here we will be having gate terminal. This polycrystalline silicon will be working as gate region, and here we will be depositing the metal layer. This works as source terminal, and the metal layer deposited here, this will be working as drain terminal, and this is the channel, and this works as bulk or body, or this can also be called as substrate. So this is a construction of depletion mode transistor. Now coming to the operation of this, because the channel is already there, in contrast to enhancement mode device, there if you want the current to be flowing in the device, if you need to turn on the device, then we need to supply a positive gate supply or positive gate voltage so that the channel will be created. And after that, when we apply a drain to source voltage, the current flows through the channel. But here, because the channel is already available, by default it is available, there is no need of VGS to be applied, or even for VGS equals to 0, the current would be flowing if we apply the required drain to source voltage. Now we will connect a positive drain to source voltage. This is VDS. Even if gate is connected to 0 volts, so the device will be conducting, right. So if I consider the VI characteristics, which is the plot of IDS versus VDS. So even for a 0 gate voltage, there would be a current flowing in the device. Now let us consider this plot. Now even for, let me write the scale here, 2, 4, 6, 8, 10 and 12. So this can be considered like 5, or let us say this is 5, 10, 15 and 20. If gate voltage is connected to 0, so I'll be having a current flowing like this. So as we go on increasing VDS, there will be linearly increasing current, and at a particular point the current starts increasing slowly, and after reaching a point called as pinch off voltage, the current becomes almost constant. So this is for VGS equals to 0. Now what if I apply a positive gate to source voltage? If I apply some positive gate to source voltage, so make sure that the substrate is also connected to a voltage held at source terminal. Now if I apply some positive VGS, then what happens? The conductivity in the channel will be increasing. Why? Because some of the electrons that are available here in the channel will be accumulated in the channel, will be attracted towards the channel because of this positive potential, and this enhances the conductivity of the channel. So what happens when I do so is the conductivity in the channel will cause a higher amount of current to flow through the device. Right? Now the opposite thing, if I connect some negative voltage, what if I connect some negative voltage at the gate terminal? Now if I introduce some negative potential here, so this will cause the charge carriers that are available in the channel to repel from the channel region. So this electrons repelling from the channel region will cause or will develop a depletion region inside the channel. So when the depletion region is created, the resistance in the channel will be increased, and in turn this will cause the IDS that is flowing in the channel to be reduced. So if I supply some negative gate to source voltage, then there will be a reduction in the drain to source voltage. Further, if I drain to source current, further if I decrease the VGS, if I make it more negative, then we can see further reduced current will be flowing in the device. So like this, if I go on decreasing, or if I go on making the gate terminal more negative with respect to source, there will be diminishing IDS available in the channel. At some particular point it will be 0 because the depletion region will be completely occupying the channel region. So the current is going to be almost 0 if the gate gets more negative potential. So this is the operation and VI characteristics of the depletion mode MOSFET. And sometimes this MOSFET will also be called as depletion enhancement MOSFET. This is all about the MOSFET devices. So in this session we have understood the construction and working of the P-type JFET and the MOSFETs. In the MOSFETs we have understood the enhancement mode MOSFET and the depletion mode MOSFETs, the construction, the operation and the VI characteristics. Thank you.